In this video, I want to have a look at Pythagoras' theorem. So Pythagoras' theorem says in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the two other sides. So what that looks like, we usually draw it up as a right-angled triangle with the hypotenuse labelled as C and the two shorter sides labelled as A and B, and we end up with C squared equals A squared plus B squared. So this result is only true for right-angled triangles. It also works the other way around though. So the converse of Pythagoras' theorem is that if the sum of the squares of two sides of a triangle is equal to the square on the third side, then it has to be a right-angled triangle. So if the three sides of a triangle satisfy this relationship, then that means that the triangle is right-angled. One piece of terminology that we do need to know is what's called a Pythagorean triad. So a Pythagorean triad is a set of three integers, so whole numbers, that satisfy Pythagoras' theorem. So the smallest Pythagorean triad is the numbers 3, 4, 5. And that's because 5 squared is equal to 3 squared plus 4 squared. So this would give us 25. 3 squared is 9 and 4 squared is 16. And 9 plus 16 is 25. The next one up is 5, 12, 13. So 5 squared plus 12 squared equals 13 squared. So those are what's called Pythagorean triads. So I want to have a look at a couple of different proofs of Pythagoras' theorem. There's lots of different ways you can do it. You can do it algebraically, you can do it geometrically, but I just want to have a look at two sort of visual ones. So if we start off with a triangle here, so we've got a right-angled triangle, this is our hypotenuse and our two shorter sides, and we've drawn on the squares there. So what Pythagoras' theorem says is that the area of this big square has to be equal to the area of this smaller square plus this other square over here. So what they've done, they've split this middle square up into 4 pieces, and we're just going to drag those and fill it into that bottom square there. So we're going to drag all those shapes down here, and we can see that it fits perfectly into this big square. So the sum of the areas of these two squares is equal to the area of this square. So that's one proof. Let's have a look at a second one. So this proof starts off with a triangle with sides A, B, and hypotenuse C. Now we're duplicating that triangle 4 times and rotating it. So this square we've got here has an area of C squared. Now we're just going to move these. So we've moved that triangle down here. So that pink shape, the red outlined one, still has an area of C squared. We've moved another one, but that shape still has an area of C squared. If we split it down along this green line, we have areas of A squared and B squared. But together they still have to equal that total of C squared. So that's a second proof of Pythagoras' theorem. The last interesting thing I wanted to show you is that when we talk about Pythagoras' theorem, we often look at a picture that looks like this. So we've got a triangle in the middle, a right-angled triangle, and we've got a square drawn on each side. And we're saying the area of 1 plus area 2 equals area 3. But it doesn't only work with squares, it can work with any regular polygon. So say we had pentagons instead, then you can still see that area 1 plus area 2 is going to be equal to that area 3. So on this one plus this one is still going to give us that. And that holds if we change the sides of our shapes as well, we're still getting that relationship holding. So it's really interesting that it does work no matter what shapes we have on there. So this program only does it with polygons, but it would work with, say, semicircles as well. So if you drew a semicircle with diameter equal to the length of each side, you'd still have that relationship of the areas, area 1 plus area 2, being equal to that third area that's off the hypotenuse. Okay, the last point is that if you're doing a question that involves Pythagoras' theorem, if you're not given a diagram, please always remember to draw one yourself.